Welcome back to my channel. This is part 2 of my infinite arithmetic series video. This is just a generalization of what we learned in that previous video. So I highly recommend watching that video because first of all, it's context to this video, and second of all, it's just an interesting proof. Very odd statement that we started with, and very interesting proof to get there. But that's enough about that video. Let's get started with this one. So I'm just going to quickly recap that video. We're going to say a series S, which is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus all the way to infinity is equal to negative 112. This is what we proved. And this is an infinite arithmetic series because of 3 reasons. It's a series because it's the sum of the terms. It's arithmetic because each pair of terms next to each other has a common difference. In this case, it's 1. And it's infinite because it goes on towards infinity, infinite terms. That's what was in last video. What is in this video though? We're going to generalize this to any series. Let's say we have some series 2 plus 5 plus 8 plus 11 all the way to infinity. We can't find the sum of that yet, even though it's an infinite arithmetic series. So this is just going to generalize it so we have a formula. I'm going to call it SA or S sub A. And it's going to be based on a term A. And this is going to be the first term. It's a variable because we don't know the starting term of the series we want. It's just going to be a general formula. So it's A, and what would the second term be? Well, this is where we introduce a new variable D. D is the common difference. Like I said, every arithmetic series has a common difference, and we can use the fact that every term is just the previous term plus the common difference. So the previous term is A, so it'll be A plus D, then A plus 2D, because A plus D is just A plus 2D, then A plus 3D, and all the way to infinity. I'm just writing the first 4 terms for now. How do we prove this? How do we get from S to S sub A? Well, like last video, we're going to be introducing some more helper series. X is a series, and it will be 1 plus negative 1 plus 1 plus negative 1 all the way to infinity. I'm just writing down a few more terms in that series. This hopefully looks familiar because this was also in the last video. We used this series to prove S, and therefore we know already that this is equal to 1/2. I'm not going to prove it in this video, so if you want the proof, you can watch the previous video. But for now, we're just going to say that this is equal to 1/2. Now, we're going to use another helper series. Since we already found out X that quickly, we're going to use Y. This is going to be a fun little series. Like S, it seems to just go to infinity and not have a finite value. It's 1 plus 1 plus 1 plus 1 all the way to infinity. How are we going to prove this sum? Well, we can use something we did in the previous video, and we can combine the series. In this case, we're adding instead of subtracting. We'll add X and Y. So basically meaning we add every term in X to every term in Y, the corresponding terms. So 1 plus 1 is 2. Hopefully that's something you learned from this video. Negative 1 plus 1 is 0. 1 plus 1 is 2. Negative 1 plus 1 is 0, and so on. All the way to infinity. Well, in a series, you can just cancel or add zeros if it's infinite, because if it's infinite, it already has infinity terms. When you cancel or add terms, it just still has infinity terms. So in this case, we can cancel off all the zeros and we're left with 2 plus 2 all the way to infinity. How can we simplify this? Well, we can factor out a 2 from every term and we're left with 2 times 1 plus 1 all the way to infinity. And hopefully this looks familiar because 1 plus 1 all the way to infinity is just Y. So this is equal to 2 times Y. Well, that's nice. All we're left with are X's and Y's. We can basically solve this like an equation. We have a Y on this side and a Y on this side, so we just subtract Y from both sides to isolate the variable. We have X is equal to Y. And since we know X has a value of 1/2, we know that Y is equal to 1/2. So we just found the sum of this series Y is equal to 1/2. Just like X, it's equal to 1/2. Fun, right? So that was the first step in determining the sum of this arithmetic series, but we're nowhere close yet. Don't worry though, we just have 2 more steps. The first thing is doing something between s and s sub a. We can first look at s, and we see that we have a 1 here, a 2 here, and a 3 here, a 4 here. That looks a bit similar to s sub a, doesn't it? We have 1d, we have 2d, we have 3d, and so on. So what if we multiply the series s by d? Since d is a variable, you can just multiply it, and we're left with d plus 2d plus 3d plus 4d all the way to infinity. Okay, so I ran out of space on the edge there, but hopefully you see the ellipses, basically saying that it's going all the way to infinity. Now, this looks very, very familiar because we know in s sub a we have d, 2d, 3d, and so on, but there's one thing that looks a bit off. In s sub a, the d appears in the second term, the 2d appears in the third term, and so on. But in s times d, the d appears in the first term. Everything seems one off. Well, remember what I said about adding and canceling zeros? Since it's an infinite series, we can just add a 0 at the front. So now there's a 0 in the first term, and d is in the second term, 2d is in the third term, and so on. Now everything fits, and we have something very similar to s sub a. What can we do next? Well, we can subtract these two because they both seem to have similar terms. We can do s sub a minus s times d, which is equal to, well, a minus 0 is just a plus d minus d is just a plus 2d minus 2d is just a plus 3d minus 3d is just a, and so on. So now we just have a bunch of a's. Similarly, we can factor this out. We can factor out an a. We're left with 1 plus 1 plus 1 all the way to infinity. And again, this looks similar to y, so this is just equal to a times y. This is our final equation. We have s sub a minus s times d is equal to a times y. This seems to have 5 variables in it. We only know 2, but that doesn't matter because since this is a formula, we don't really care much about the variables. As long as we have enough knowns, we can actually solve for it. Right now we know s and we know y, so we can go ahead and plug those in. I'm going to use this space again. S sub a minus, and we know s is equal to negative 1/12 times d is equal to a, or I'll use the same line actually, a times 1/2. Now, all we have to do is we have to add this term to both sides right here. We have to add this to both sides because there's a minus here. We add to both sides and we're left with s sub a is equal to 1/2 a minus 1/12 d. And that, my friends, is our final answer. I'm just going to box it right here because this is what we were looking for all the time. This is how we derived the general formula. I'm going to erase the rest of my work. And now that I've done that, let me just write that here. We have 1/2 a minus 1/12 d. This is our formula. That's what we proved today. And let me just try plugging in something. So let's say we have that series from the start, 2, 5, 8, 11, all the way to infinity. This has an initial term of 2. This has a common difference of 3. So if we plug that into the formula, we get 1/2 a. So a is 2, so 1/2 of that would be 1. And minus 1/12 d. So d is 3, so 1/12 of that would be 1/4. So 1 minus 1/4 is equal to 3/4, and that would be a sample answer. So thank you for your patience. We finally proved it, and I'll see you in our next video which will most likely be a content video rather than a specials video. Our next specials video would be an interesting proof, but this time it'll be something that is proved wrong. And I'll see if you can catch the error in the middle, and then I'll explain the error at the end. So it'll still be interesting, but instead of proving something true, it'll be proving something false. So with that, see you next time. Bye.